Welcome to G Fun Facts Online. High above us in the silent black void, thousands of satellites are our technological sentinels. They are our global communication network, our weather forecasters, and our eyes on the universe. But this tranquil environment hides an invisible, constant threat, a relentless barrage of charged particles and radiation that can build up on a satellite until it unleashes a catastrophic electrical discharge, a miniature lightning strike with the power to cripple or kill our vital orbital assets. Today, we're diving into the science of protecting satellites from these invisible electrical storms, a critical and constantly evolving field of engineering. Let's start with the environment itself. Space isn't truly empty. Orbiting spacecraft are immersed in a sea of plasma, a state of matter made of free-floating ions and electrons. Starting at about 90 kilometers up, solar radiation is intense enough to ionize molecules in the thin upper atmosphere, creating this electrically charged soup. The density and temperature of this plasma change with altitude and location, directly impacting how quickly a satellite will charge up. The main culprit for this hazardous environment is our own sun. It's not just a benign source of light and heat, it's a major contributor to the dangers. Solar flares, which are sudden, violent bursts of radiation from the sun's corona, can dramatically alter the space environment in an instant. These events spew out a torrent of X-rays, gamma rays, and high-energy protons. When this storm of particles hits Earth's magnetosphere, it can trigger what we call a geomagnetic storm. During these storms, the number of energetic electrons in certain orbits can skyrocket, massively intensifying the charging process. Different orbits carry different risks. Geosynchronous orbits, or GEO, are about 36,000 kilometers up. This is where many of our big communication and weather satellites live, and it's a particularly nasty spot for severe charging, especially during those geomagnetic storms. Satellites in low Earth orbit, or LEO, have it a bit easier, but they still face charging risks when they pass over the polar regions or through the Earth's shadow at night. While Earth's magnetic field does offer some protection, it also creates its own hazards by trapping high-energy particles in regions known as the Van Allen belts. These donut-shaped zones of intense radiation are a deadly obstacle course that some satellites must navigate. So how does a satellite actually accumulate this charge? This process, called spacecraft charging, happens through a few key mechanisms. The most straightforward is the direct collection of particles. The satellite is constantly being hit by the ions and electrons of the surrounding plasma. Because electrons are about 2,000 times less massive than protons, they move much faster. This means far more electrons hit the satellite's surface than ions, leading to a natural tendency for the spacecraft to build up a negative charge. But it's not the only thing happening. Sunlight itself plays a role. When sunlight, especially its ultraviolet component, strikes a satellite's surface, it has enough energy to knock electrons loose. This is called photoelectric emission, and it leaves behind a positive charge on the illuminated parts of the satellite. So a satellite's orientation to the sun becomes a critical factor in its overall charge. Then there's secondary electron emission. When high-energy particles from the space environment smash into a satellite's surface, they can dislodge even more electrons. Depending on the energy of the incoming particle and the surface material, this can either add to or subtract from the satellite's net charge. It's a complex interplay between these three forces: electrons coming in, electrons being knocked out by sunlight, and electrons being knocked out by other particles. When the flow of charge to and from the spacecraft reaches an equilibrium, the satellite is said to have reached its floating potential. But this potential is rarely uniform across the entire satellite, and that's where the real danger begins. This leads us to the different types of spacecraft charging, each posing its own unique challenge. The first is surface charging. This is the buildup of charge on the outside of the spacecraft, caused by particles with energies in the kilo-electron-volt range. If a satellite were a simple sphere made of a single conductive metal, the whole thing would charge to one uniform voltage. We call this absolute charging. But satellites are anything but simple. They are complex machines built from a mix of conductive metals and insulating, or dielectric, materials like thermal blankets, solar panel cover glasses, and antennas. These different materials react differently to the space environment, which leads to a dangerous condition called differential charging. This is where different parts of the satellite accumulate different amounts of charge and exist at different electrical potentials. For example, a part of the satellite basking in sunlight might become positively charged due to photoemission, while a shaded section right next to it continues to build up a negative charge from collecting ambient electrons. This potential difference, this voltage gradient between adjacent surfaces, can create incredibly intense electric fields across the skin of the spacecraft. But there's a more insidious form of charging called deep dielectric charging, or internal charging. This happens when extremely high-energy electrons, with energies in the mega-electron volt range, penetrate the spacecraft's outer skin. These are the particles you find in the Van Allen belts or during a major solar storm. They are so energetic, they can blast right through the outer shielding and become embedded deep inside dielectric materials, things like circuit boards, the insulation around cables, and other plastic components. Since dielectrics are, by definition, terrible conductors of electricity, these embedded charges have nowhere to go. They get trapped. Over days or weeks, the continuous bombardment can lead to a massive buildup of charge buried inside a component. This internal accumulation can generate electric fields so powerful they exceed the material's dielectric strength, which is the maximum electric field it can handle before it breaks down. This is a huge concern for any satellite whose orbit passes through the Earth's radiation belts. The charge itself, whether on the surface or buried deep inside, isn't the problem. The real danger is the sudden, violent release of this stored energy. This is called an electrostatic discharge, or ESD. It's a miniature lightning strike, and it's the primary way spacecraft charging damages and destroys satellites. The consequences can range from a minor glitch to total mission failure. When the electric field from differential charging or deep dielectric charging becomes too great, it can trigger an arc discharge. These arcs can physically damage the spacecraft. One type is a punch-through, where a charged-up insulating surface arcs through the material to the grounded metal structure underneath it, literally punching a hole. Another is a flashover, where the arc jumps across the vacuum of space between two differently charged surfaces on the satellite's exterior. These arcs can vaporize thermal coatings and damage solar arrays, leading to overheating and power loss. But the damage isn't just physical. An ESD event is a rapid high-current blast that generates a powerful electromagnetic pulse, or EMP. This pulse travels through the satellite structure and can couple into its wiring, wreaking havoc on its electronics. This is called electromagnetic interference, or EMI. As our electronics have gotten smaller and more powerful, they've also become more vulnerable to this kind of interference. An EMP from a discharge can cause transient errors, flipping bits in a computer's memory, and corrupting data. It can create phantom commands, where the onboard computer mistakes the electrical noise for a valid instruction, causing the satellite to perform an unplanned maneuver. In more severe cases, the high currents can permanently fry sensitive components, leading to a partial or total loss of a system. The history of spaceflight is filled with cautionary tales. In 2010, the communications satellite Galaxy 15 was zapped by a geomagnetic storm. The discharge disrupted its command systems, turning it into a zombie sat that drifted uncontrollably across the sky for 8 agonizing months, threatening other satellites in its path. In 2003, the Japanese Eidos 2 environmental satellite was completely lost after a powerful solar flare. The culprit is believed to have been deep dielectric charging that led to a catastrophic discharge, crippling the spacecraft. These failures have taught engineers hard lessons and driven the development of sophisticated defenses. Recognizing this threat, engineers have developed a multi-layered defense strategy. The first line of defense is passive mitigation, features built into the very design of the spacecraft. A primary strategy is to make the satellite's exterior as electrically conductive as possible. This is done by applying thin, transparent conductive coatings, like indium tin oxide, to insulating surfaces, like solar cells and camera lenses. This conductive layer allows charge to spread out and equalize, preventing the buildup of large potential differences. Proper grounding is also essential. All conductive parts of the spacecraft, the main structure, thermal blankets, component housings, are electrically bonded together to a common spacecraft ground. This effectively turns the satellite into one large, unified conductive body. And of course, there is shielding. Critical electronics are encased in materials like aluminum or tantalum. The shielding absorbs a significant portion of incoming radiation, and it's the main defense against deep dielectric charging, stopping those high-energy electrons before they can bury themselves in sensitive components. But sometimes, passive measures aren't enough, especially during severe space weather. This is where active mitigation comes in. These are systems that can be turned on to fight back against charge buildup. One such device is a plasma contactor. It emits a cloud of low-energy plasma around the satellite, which effectively neutralizes the charge that has accumulated on its surfaces, bringing the spacecraft's potential back in line with the surrounding space. Other systems include electron and ion emitters, essentially guns that can actively fire beams of particles to discharge a spacecraft that has become too negatively or positively charged. Beyond preventing the discharge itself, another crucial strategy is making the electronics more resilient in the first place. This is known as radiation hardening. It involves using specially designed and manufactured electronic components that are inherently resistant to radiation damage. These rad-hard components are incredibly robust, but can cost up to 100 times more than their commercial counterparts. Engineers also design systems with redundancy, incorporating backup systems for critical functions, so that if one component is zapped, a backup can take over. Before any satellite is launched, it undergoes brutal testing on Earth to ensure it can survive. Components, and sometimes entire small satellites, are placed in vacuum chambers and blasted with electron and ion beams to simulate the space plasma. Engineers use specialized equipment to deliberately inject powerful electrical discharges into the satellite structure, monitoring its systems to see if they glitch or fail, ensuring the protective measures work as designed. This is all supplemented by sophisticated computer models that can predict how a satellite will charge in different orbits, allowing engineers to spot and fix potential problems long before any hardware is ever built. As we push into new frontiers and become ever more dependent on our orbital infrastructure, this invisible battle will continue. Researchers are developing new materials with tailored electrical properties, including self-healing surfaces that can recover from discharge damage. And by better understanding the link between the electron environment and discharge events, we are getting closer to being able to forecast periods of high risk. This would allow satellite operators to take preemptive action, like temporarily powering down non-essential systems to ride out the worst of a space weather storm. The challenge of protecting satellites from electrical discharge is a constant, complex struggle against an invisible foe. It's a field that demands a deep understanding of plasma physics, materials, science, and electronics engineering. As we continue to expand our presence in space, these innovations will be the bedrock of mission success, ensuring our sentinels in the sky remain resilient against the silent, electrical storms of the cosmos.